is actually the difference between the value, V naught, minus the equity. Just from the same formula of value of asset minus debt gives me equity. So we can find out, and we know that the market value of debt is 9.4. Also, we can find the present value of debt by discounting the future debt to today, and we have it as 9.5. Now the expected loss is given as 1.2. I haven't solved for that, which is this at this point. Then the expected recovery is just the difference of this and that, and you have that you can recover 91% of whatever you invest into that scenario that we have. A simpler way of looking at it, because I know mathematicians want like a simpler way, we have this setup, and with that we can find out that it's the same thing very much, which is the recovery rate if there's any in the event of any default. Now going on to one of the most important parts of this paper, which is the estimating. The first case we did was just for companies. Now what about individuals? If an individual comes to a finance company and they want a loan, a mortgage, how do I know if this individual is going to pay me back? How much do I know that I'm going to charge it for the interest rate? So this tool is very important to do that. So we'll go back again. For an individual, we have to think of the optimal strategy of an individual in his wealth situation. Now, I wrote this down from earlier and I can write it down again. It's just kind of like the situation of an individual basically. An individual is basically this equation. I'm going to explain it later on. 1 minus eta dt plus alpha eta y, so yt r, then you have yt sigma dw plus mu dt minus this. This is the basic one, dt. This is just one value. If you have wealth, some part of your wealth goes into risky asset. Some other part goes, this is the one that goes into risk-free asset. I put it in the savings account. Some other part goes into risky asset. And the final part is just my consumption. As much as I'm investing, I have to eat, right? So that's also a part of it. And later on, we'll introduce one other part of it, which is called the wage, which is also subject to time. Even though I inherited some money, I invested some of them in risk-free, another one in risky asset, then I'm still working. If I'm working, I'm going to make a salary, which is the wage, right? It's going to add to my wealth. Then, finally, I can take away my consumption from it. So we're going to talk a lot more about that. So going on, I defined some of these parameters from the geometric Brownian motion. I took the derivative of the geometric Brownian motion using Ito's lemma. Of course, Ito's formula, most of them were applied into it. If you look at the paper, it's there. Then, now, this is the solution that I got. The y tilde t is a solution. This y tilde t is a solution of this equation, which is kind of like similar to what I have there. But this is a similar scenario than the one I have there. And now, let's now think of solving this problem, which is this basic problem in the deterministic case. Everybody likes a smooth case where it's a controlled experiment and we can easily get good answers. So now if we try to do that, the stochastic part goes away because it's deterministic. So we only focus on this part and the consumption part, and this is what we have. And if we solve for that, it's just a first order differential equation. We'll arrive at this solution. That's just showing the solution of the stochastic part and the deterministic part. Now, going to what I just said earlier, it's called the optimal portfolio and selection, optimal portfolio selection and consumption. Every individual wants to know how to manage their lives. I want to know, if I meet a finance consultant right now, how much, okay, I just inherited money, $1 million from my parents. How much do I put into risky asset? How much do I put into risk-free asset? And I become a professor, so I'm still making money. how much do I keep? How do I manage this money? How much do I consume? So that's what made this guy, his name is Robert Cohn, is in NYU, to propose this. He actually looked at, he actually followed Merton's paper, and he presented Merton's paper in an interesting finance scenario. So he created some control problems where an investor starts with an initial value Y, it's not supposed to be X, at any time T. And he said, eta, let eta represent one fraction of his wealth that goes into risky asset. The other fraction goes into risk-free asset, right? Now, and he also mentioned consumption, where this eta, if I invest one fraction, eta is of course constrained between 0 and 1. Because if I invest one fraction in risk-free, the other fraction goes to risky. And consumption, of course, is greater than 0. Nobody does negative consumption. Everybody has to consume. So, and now he now set it up with this differential equation 4 that I have there. Now he solved this equation with the controls. He solved the HJB equations. It's in the paper with the controls. I explained the details. And a utility function. Now I'm going to mention utility. A utility function is actually a monotonic increasing function that is concave down. Why? Now, if this is utility, it's satisfaction. Utility is actually satisfaction. And this is time. Now, if I have a small amount of money, okay, I'm drinking water. I have a glass full of water. The first sip is always very great. I have like so much satisfaction. By the time I get to half of it, I still have some satisfaction. By the time I get to the end of that cup, I almost have maximum satisfaction, right? By the time I go into 3 cups, my satisfaction peaks. I don't get any satisfaction anymore. And that's what the utility function actually represents. So he solved the utility function and the HJB, and he came with optimal controls, meaning this fraction of wealth, which is this, an optimal control for the consumption rate, which was that. So we're going to use some of the work that he did, and we're going to apply it in our case. Now, going into what he did, we want to compare it with what we have for our own individual wealth equation. So now, because of what he did, our volatility changes from just being sigma y, which was in the case of the company, to now sigma y, eta y, because of the controls that he put into the situation. Now, we put it back. Now, this probability function that we see here, this actually just represents our wealth solution that was solved earlier. For a company to default, the wealth has, the value of your asset right now has to be less than your debt. If I have $500,000 and I have to pay back $1 million, that's it. I'm not going to pay. I'm going to default, and that's the condition that I have here. And we're going to do that. We're going to try to estimate that. So now, before we go on, there's this value on this side, this integral that I have. It's stochastic. I need to find an estimation for it because it's difficult to kind of work with this value. So because of that, I'm gonna give that value CT. If I give the value CT and I take an expected value, an expected expectation on it, and I solve for it, and I make CT, which is a normal distribution when I take the expectation, with mean 0 and standard deviation S, and I solve for it, in the end, I will have this solution for CT. Most of you will ask me, why can't I can still solve for that, right? Because I had that problem with my professor too. I was like, I can still solve for that. If this is a constant, I can still take the integral of this. And he said, no, because of Robert Kuhn's work that we did. Because some, like eta, is embedded inside of alpha. So it's not technically a constant. Some of eta is embedded in alpha. So this alpha is not technically a constant. So that's why we just left the approximation at this point, and that's why I made that alpha s, which is this consumption, is not actually a constant. So we leave the approximation at this point, and we move on. So we're going to do the same thing that we did in the case of the company. We have x as this. If we properly do it, then we have the probability. Just in the case of the company, we don't need to do it. There's nothing different. It's just that the v naught changes to y naught minus ct, and everything else is the same. And if we solve that, we have the probability of default, which is this. And this probability of default, like I said, is very important, because you can estimate. If a guy comes to you and you want to give him money, you can use this to estimate if you should give him the money, or how soon it's going to default at any time t. So going on, the individual equation is the same thing again. Now, if I do the same thing that I did in the case of the company, this is kind of like the first equation in the case of the company, where this represents our v naught. But for the individual, this would be my v naught. And everything else is just the same, pretty much. And my dt, my d1 and d2, of course, it has to factor in also the fact that this is v. That's it. Everything else is the same. So moving on. Now, if I'm going to incorporate wage, like I said earlier, the initial equation, you remember, that I wrote was just this. Now, if I'm putting in wages, because I'm going to make money, the whole equation just changes. Everywhere in the initial equation, here, okay, in the initial equation here, where I had y naught minus alpha ct, it's now going to be y naught plus beta minus alpha ct, because now I can join these two together and they become beta minus alpha, or dt. That's it. That's the only thing that changes, and everything else remains the same. So, and everything else is just the same. It's the same thing. So going on, I have probability of default at any time t. It's the same probability of default, which we did in the case of the bond prices and the historical data, which we've already completed. Now, the second part, the second probability of default, is that we've been assuming that it's a risk-neutral rate, which is R. Now, what if it's a real-world rate? Risk-neutral rate is, okay, there's no risk. But what if it's a real-world rate? The only difference is that my R will just change to mu. Every R that I had in that will just change to mu. And this will give me, this will be my real-world probability of default. Nothing else changes. It's just the R changes to mu.
But the equation doesn't change at all?
Yeah, not really. So going on, I have, now if I want to calculate individual probability of default, it's the same equation that I derived from earlier. All I need to change, my Q from the individual equation is just this. And now I can solve for lambda, which is just my default intensity. And if I do it, because this is kind of like a density function, in the end, this is what I'll come up with. I had to put in GT for the whole of this, so it can be easily seen that this comes to that. Then my GT is this, and here I have a derivative here. So which I said in the second part that it is all of that. That's the derivative. So moving on, I have the risk premium. Why are we doing this part? This is one of the most important parts. Because if I'm taking a risk, I want the return. I would rather put my money in the bank than give it to this guy. So if I'm gonna give, he's gonna give me 10%, and I don't know what he's doing, I have to be careful. But also, so for companies, this is how they estimate their premium. The premium is just what I get, the extra thing I get for taking a risk. That's it.